All right. So, one of the reasons Pluto is called a dwarf planet, because the gravitational attraction between them makes them go around a point that's about right there. Right? So, it would be wrong to think of Charon goes around Pluto. Because they are similar in size and because they attract each other the same, it's more like it's a little child and a grown-up playing Ring Around the Rosie or something like that and swinging each other around. Right? So the grown-up is big enough that they don't move as much, but they're still off center of where everybody's swinging, while the child is further away from where you're swinging. And so Pluto, if you watched it, would go in a circle like that, while Charon would go in a big circle like that. This is one of the reasons we've reclassified Pluto as a dwarf planet, simply because it does not dominate its moon the way every single other planet that has a moon does. Right? All right, so back to what how gravity works. Now, there's a guy named Newton. We talked about him a little bit last time. So Newton has 3 laws that he came up with, 3 laws of motion. The first is, Newton's first law is a body at rest will remain at rest, or a body in motion will remain in motion in a straight line unless acted upon by external forces. Right? So, unless something pushes on it during this class period, your cup is going to stay right there. Right? Or if there were no friction or anything like that, and I took a ball and I started rolling it, it would just keep going until something else did something to it. Right? So if we were in outer space with no planets or anything around, and I just threw something, it would take off and just keep going in a straight line. Right? And it would keep doing that until something else did something to it. Now, I would also be headed in a straight line the other way. Right? But not as fast, depending on this mass of the object. So Newton's first law is all about external forces. Now, this is where it's important. You exert 210 pounds of force on the Earth exerts 210 pounds of force on you. That's why you're not going anywhere. Right? Because the forces balance out. Or the floor exerts 210 pounds up on me, I exert 210 pounds down on the floor. Now, if the floor wasn't doing its half of the job, what would happen to me? I'd fall through. Right? So, Newton's first law has to do with forces. Doesn't mean there are no forces. It means whatever forces there are balanced. Right? So, here, if we have a ball moving along, right? Well, when it gets here, the forces are no longer balanced, it speeds up. But if it's in this situation going along a flat floor, its speed stays the same. Or if it's here, where it heads up a slope, it slows down. Right? Because there are external forces acting on it, in this case, gravity in particular. Have you ever been swinging something in a circle and let go of it? Right? What does it do? Right. It doesn't go out away from you. It goes whatever direction it was heading when you let go of it. This is how a sling works, right? You get it going and you let go. So the object, this object is going that way. The force of the string on it is making it go in a curve. If the string breaks, it's going to keep going straight along the direction it was going when the string broke. Right? Right? If you come around here and the string breaks right here, it's going to keep going straight. not going to go that way. It's going to go straight. Does that make sense? This is important because this is a big part of why we go in a circle in orbit. So this is another thing Newton sort of went through. Newton said he had a Gedanken experiment. An experiment you create in your head, right? You just think through it. So he had an experiment where he created in his head, and he took a cannon, he thought about a cannon. And you fire a cannonball that's kind of slow, and it does this. And you fire one that's fast, and it does that. And Newton imagined, well, if I get up on a high mountain and I keep firing this faster and faster and faster, right? And faster, does it ever reach a point where it misses the Earth and simply comes back around? Right? The key to flying is throwing yourself at the ground and missing. Right? And that was his thought experiment. Can I fire this fast enough that it will simply curve in such a way that it never actually hits the ground? And the answer is yes. Right? The answer is yes. Once you have done this, you've reached what we call now the orbital velocity. You've reached the velocity at which you will just go around the planet. Now, you can't do this with an actual cannonball in the atmosphere because the air is going to slow you down, right? But once you get up out of the atmosphere, you can do it. The reason old satellites eventually fall is the atmosphere doesn't have a hard, oh, here's where it ends, right? And so satellites that are not far enough out are still hitting just a little bit of atmosphere. And over a long period of time, that slows them down. And as they slow down, they come down lower and lower, right? Eventually, they're not going fast enough to continue to work. All right. We've already talked some about Newton's first law, and we talked some about his third law, which is equal and opposite reactions. But now, if we exert a force on something, right? If we exert a force on it, the acceleration goes as the force equals its mass times the acceleration, right? So, if I take an empty shopping cart and I push it really hard, it goes really fast, right? If I take a full shopping cart and I push it really hard, it doesn't go as fast. Right? Because it has more mass, I'm using the same force, because mass went up, the acceleration went down as I fill up the cart. This is Newton's second law, that the force, the net external force on an object results in acceleration that is force equals mass times acceleration. All right? Now, putting all this together, along with his thought experiment about firing a cannonball, Newton came up with, well, this plus observations from planets and moons around other planets, right? He came up with, how does gravity behave? Now, discovering gravity is actually a pretty phenomenal thing, because gravity it's everywhere, right? You don't see it, you simply feel the results of it, but coming up with, hey, there's something called gravity that's doing this, is a real tough thing to do, right? And it's hard to imagine, if you've never heard of gravity, what it would take to think about and come up with gravity. So, gravitational attraction of two masses. So if this was Charon and this is Pluto, gravitational force between them is this gravitational constant times the masses multiplied together divided by the distance between them squared. Right? So here's the distance between them. Take the distance, square it. So the force is gmm over d squared. Right? Now, there's a gravitational attraction between my phone and this remote. Right? They have gravitational attraction. There's a force between them due to gravity, but it's really small. Why? Because this number, the gravitational constant, is very small, 10 to the minus 11. Right? Because that constant's very small, we don't notice gravitational attraction between ordinary objects. Because the gravitational attraction between them compared to, say, just the friction or the air moving around and things like that is still pretty small. But this is where that I exert 210 pounds of force on the Earth exerts 210 pounds of force on me, comes into play. This is the mass of the Earth, this is the mass of me. This is the distance between me and the center of the Earth, right? Which is where we consider the Earth to be, at its center, and there's the gravitational constant. Doesn't matter which one of these you're talking about, the force is the same. So the force this way and the force that way are exactly the same. That's why Pluto orbits in a little circle, Charon orbits in a big circle. Why? Pluto's bigger. So while we have the same force on both Pluto and Charon, Pluto is able to force Charon to go all the way around, while Charon only forces Pluto to move a little bit. All right? So, straightforward. Questions on the math? Everybody know how to punch this into their calculator? 6.67 times 10 to the minus 11. If you don't know how to punch that into your calculator, find me in my office, bring your calculator, and we'll go over it. All right? We're going to be dealing with, as you can imagine, the mass of the Earth is a big number, right? So we're going to be dealing in astronomy with big and small numbers all the time. So if you're struggling with your calculator on these, come by and we'll work with your calculator on showing you how to do it. All right. Newton's third law of motion, equal and opposite forces, right? For every action, there's an equal and opposite reaction. So, have you ever done the stand on a, thank you. This is two kids standing on skateboards and they push on each other and they both go off in different directions, right? We've all done something similar, playing around with shopping carts or something, right? You've done this experiment, most of you, at some point. Guys are slightly more likely than girls to have done this experiment. All right? You can do it in a boat, right? Two people in different boats push off from each other and head out in separate, opposite directions. And again, your acceleration depends on the relative masses. Okay, so now we get to something that we use all the time in astronomy, which is measuring the mass of an object based on how things orbit around it. Right? When I'm whirling a ball on a string, right? When I'm whirling a ball on a string, the force the string is exerting on the ball goes as the mass of the ball times the velocity squared divided by the length of the string. It's called centripetal acceleration or centripetal force, right? So as I whirl it, the force that I'm exerting on it to make it go around depends only on its mass, the length of the string, and the velocity. So if I whirl it faster, right, the string has more force on it. If I whirl it slower, the string has less force on it. If I put a heavier mass on it, the string has more force on it, right? Gravity, when something is in orbit, gravity is what's providing the force. It's like the string holding you in place as you go in a circle. Gravity is the force making you go in a circle, right? Gravity is that force. And so all we really do in the next slide is we set these two things equal to each other and we solve for the velocity. Right? So the velocity, the orbital velocity of an object. The orbital velocity of an object depends on gravitational constant, the mass of the object it's going around, and its distance from the center of mass of the object it's going around. So if these two objects were out in space, right, my phone and the remote, and the remote were going around my phone, right? We could measure, using a telescope, we could measure how fast the remote is going around my phone. With a telescope, we could measure how far away the remote is from my phone, right? And using those, we could measure the mass of my phone. Because we would have measured this velocity, we would have measured that distance. I need to put this, I'll redo this slide and solve for the mass, right? We know this, and so the only thing we don't know is the mass of my phone, right? And so as we measure the velocity of the remote around my phone, we end up figuring out what the mass of my phone is. This is actually how we figure out the mass of a lot of things that are far away. Because this velocity, right? The velocity, yeah?
What's the difference between the small m and the big M?
The big M usually stands for the mass of a planet or the mass of a sun. Small m is usually the mass of what's going around it.
Okay.
That's all, right? All it really is big object, little object,
Makes sense.
right? So, the velocity of anything going around the Earth, right? All these satellites up in Earth orbiting around. Their velocity depends only on what? The mass of the Earth and how far away they are. Right? Mass of the Earth and how far away they are. That means what? Everything in the same orbit is going the same speed. Everything in the same orbit is going the same speed. Right? This is the one thing that bothered me about the movie Gravity. Who saw Gravity? If you haven't seen Gravity, I hope to have it here in the planetarium sometime. You can see it there, right? But the movie Gravity, the premise is there's a an accident in space, this debris comes flying through, hits the astronauts and the shuttle, and everything goes sideways all over the place, right? And then all that debris comes back around and hits them again. Now this was a big surprise to me because I know orbital mechanics, and in my head, oh, it hit them once, it's not going to hit them again. Why? It's going a different velocity. Because it's doing a different velocity, that means it's heading to a different orbit. Right? It's not going to be in the same orbit, but the basic premise of the movie was this stuff was coming around again and again and again. I had to live with it. It's like, all right, I'll take that. The filmography was great, so I could forgive them their physics error. Right? But because the debris was going a different velocity, it was headed for a different orbit. And it would never have hit them a second time. Right? It would have been out further, it would have slowed down as it went out, and would have ended up in a higher orbit. Another thing from the movie Gravity, right, has to do with forces and mass. If for some reason you're ever stuck in space and all you have is a fire extinguisher to propel yourself with, right, you want to turn it upside down so that the nozzle is at your center of mass. The reason you want to do that is, what happens if you push me real hard on my shoulders? I flip over backwards, right? So if I'm in space and I hold it like this, I spin. But if I put it in my center of mass, it pushes me, right? I don't spin. So you want it at your center of mass so that you don't spin. If you're ever caught in space and just have a fire extinguisher to move around with, right? Just keep that in mind. Since we are talking about forces and everything, so, and all of these are all the different variables, right, that showed up. Here I say the small m is the mass of the orbiting body, and the big M is the mass of the orbited body. But like with Charon and Pluto, right, they actually both orbit a spot that's in between them somewhere. Now, the Earth and the Moon system, our moon is, you know, farther out, smaller relative to the Earth. The Earth is big enough that the point that they both orbit around is inside the Earth. So if you look, we're way out in space watching the Earth and Moon go around, you see the Earth wobble a little bit as the Moon went around it, but not like Pluto, where it goes in a circle like this. All right? Does that make sense? Okay. So, if we look at these equations, we can pull out this piece. Remember the force, forgot to bring a pen today, right on here. Remember, force is mass times acceleration, right? So if I say force equals my mass times the acceleration of gravity, and I stick my mass here, we're back to, this is the gravitational force, G(m)m) over r squared. So we pull this out, this G out, that's just this, and call it the gravitational acceleration at the surface of a planet, or at the surface of a moon, or at the surface of whatever. You take the mass of the moon, you take the radius, right, and you just do the calculation, and you get the gravitational acceleration. If you want to know how much force the planet exerts on you, you just multiply by your mass, and you get the force that the planet exerts on you. Gravitational acceleration of the Earth is 9.8 meters per second squared. Right? On the surface of the Earth. Now, as we go up onto a mountain, it goes down just a little bit. Not a lot, just a little bit. And if we go to Death Valley, you go up just a little bit. You go to the moon, the mass of the moon and its radius are different, but it ends up being, the surface gravity of the moon is about 1/6 of the gravity here. Right? It's a weight loss program, but it doesn't make me any smaller. This is why people talk about, I don't know if you guys did not. Have you ever watched film of astronauts on the moon? You know, and they bounce, right? There's gravitational acceleration. Then they had to take golf clubs and a golf ball and hit a golf ball on the moon. Just cause, right? Hit it a lot further. All right. So, if you decide to leave the Earth, right? Decide you just want to go off into space, you have to overcome the gravity of the Earth, right? Every time we launch a rocket, it has to overcome the gravity of the Earth. If it doesn't, it just does this, right? It is, I actually know some guys that do this all the time. When I was a grad